Hello everyone, my name is Xingxin Tan. I am from University of Washington, Seattle, and thank you for coming to my DAMOP 2022 talk today. I'm really grateful for this opportunity to share with you our team's observation of many-body dynamical delocalization in a kicked 1D gas. The quantum kicked rotor is a great tool to study quantum chaos and interaction-driven quantum dynamics. It also allows us to perform quantum simulation of the Anderson model in the synthetic momentum space, as well as to study the metal-to-insulator transition. The classical version of the kicked rotor is the textbook paradigm for classical chaos. Imagine a pendulum with periodic delta kicks of gravity-like potential. The Hamiltonian of the system looks like this. This time-dependent Hamiltonian may seem daunting at first sight, but the model actually boils down to a single, unitless parameter, the kick strength k. For k much larger than 1, in the long time limit, the momentum undergoes random walk, and the kinetic energy growth becomes diffusive, which means it grows linearly in time. In the quantum version, the reduced Planck constant h bar introduces an additional parameter into the system, the unitless kick period tau. It turns out that tau itself has a periodicity of 4 pi. The quantum-kicked rotor can be realized in ultracold atoms as the atom optics kicked rotor, where the periodicity of tau manifests as the temporal tau effect. What's really interesting is that when tau is an irrational multiple of 4 pi in the long time limit, the kinetic energy of the quantum-kicked rotor saturates and stops growing, no matter how hard we kick or how many kicks we have. This is known as the dynamical localization in the momentum space, which can be mathematically compared to the Anderson localization in condensed matter physics. In condensed matter systems, the Anderson localization is a localization in real space. Here on the left, I have made a rough sketch of a 1D lattice, where the vertical axis is the lattice potential and the horizontal axis is the location in the lattice. The randomness of the lattice depth at each site leads to the destructive interference in wave functions when particles attempt to tunnel between adjacent sites, which then halts the transport in the long time limit. On the other hand, in the quantum-kicked rotor, the dynamical localization is a localization in momentum space. Here on the right is a sketch of the momentum lattice. The vertical axis is the lattice potential, and the horizontal axis is the momentum. During the infinitesimal time that each delta kick happens, the diffraction mixes up different momentum states, which can be compared to the tunneling in the Anderson model. But during the time period between the adjacent kicks, particles in each momentum state accumulates a phase proportional to the kick period. If the phase accumulation is an irrational multiple of 2 pi, then the continued accumulation of these phases becomes a pseudo-random number under modulo 2 pi arithmetic, which leads to the localization in the momentum space. So far, we've established a solid ground on the non-interacting quantum-kicked rotor, but the nonlinear many-body interaction in mean field theories is predicted to result in a region of dynamical delocalization with a sub-diffusive energy growth. This is in direct contrast to the linear energy growth in classical chaos and the zero energy growth in non-interacting quantum-kicked rotor. Meanwhile, non-perturbative theories like the work by Rylance et al. In 2020 predict that the 1D interacting quantum-kicked rotor should still localize. After a long history of theoretical work in the literature, our team reported the first experimental realization of interacting quantum-kicked rotor, concurrent with the complementary work in David Wells' group at UCSB. Our observation probes the regions with theory contradictions, and we have observed the sub-diffusive energy growth in our experiments. Our experiment created 1D 174 ytterbium ultracold gas by using 2 arms of the infrared lattice light in the x and y direction to provide constant standing wave confinement and squeeze the ytterbium gas into 1D tubes. A third arm of the lattice light in the z direction is flashed in a pulse wave manner shown at the bottom to provide the delta kicks along the length of the 1D tubes. The confinement power in the xy direction controls the many-body interaction strength Gn, while the pulsing power in the z direction controls the kick strength K. Here is our data showing the comparison between localization and delocalization. With weak interactions on the top row, we are seeing the localization in the momentum distribution. On the top left is a series of absorption images where the vertical axis is the momentum distribution and the horizontal axis is the number of pulses, or equivalently, the time. We can see that for weak interactions, the axial momentum distribution remains the same in the long time limit. However, with strong interactions in the middle row, we are seeing the delocalization in the momentum distribution after a while. At the bottom, figure G shows the average kinetic energy versus pulse number +1 in log-log scale. For the purple circles with weak interactions, the kinetic energy saturates in the long time limit. But for the red squares with strong interactions, the kinetic energy grows like a straight line in the log-log plot, and that is a power law relationship. Our power law fit, which is the black line in figure G, returns a sub-diffusive exponent of 0.36. Here's our data of delocalization versus different kick strength, where we see different onsets of delocalization, as well as different power law exponents. Here's our data of delocalization versus different interaction strength, where again we see different onsets and different power law exponents. All these sets of data can be put into a bigger picture in this phase diagram in the bottom right corner here. With different kick strength K and different interaction strength Gn1d, the mean field theory predicts a region of dynamical localization and another region of dynamical delocalization separated by a boundary of transition. And that is my presentation on our work in 1D quantum-kicked rotor. Thank you for listening and stay tuned for our latest work on quasi-periodic quantum rotor by my colleague Junhui Sito.